In this video, we are going to explore finite state machines from the viewpoint of mathematics. Mathematically, a state machine is much like a monoid. Now, a monoid is something that you learned about in an algebraic structures class. In case you have no idea about what monoids are, this part of the lecture may be a little bit difficult for you, so I will go light on that. But let's just know the definition of monoid. A monoid is a set M together with a binary operation defined on it, like say addition or multiplication or some such thing, such that it satisfies two properties. Number one, it is associative, and number two, it has an identity element. Let's look at an example. Suppose my set is the set of all non-negative integers and my operation is usual addition. Then we know it is an associative binary operation and the identity is obviously 0. If you add 0 to anything from left or from right, the number remains unchanged. Now here is another example. All finite length words using some letters, say letters ABC. So what's a finite length word? Something like ABC or AAA or ABCA, something like that. And the operation is concatenation. ABC followed by AB is just ABC, AB. And you can easily guess that the identity here is the empty word, the word of length 0. That's also a finite length word, because if you concatenate the empty word with anything, it remains the same. Now, a priori, it may not be at all obvious how a monoid can be linked with a finite state machine. So let's take a look at that. To understand, we again take the example of our Humpty Dumpty, except that this time I am not showing the outputs, because as we have already discussed in our example on C comments, the outputs are more of a cosmetic thing put on the structure which is given by this transition diagram. So we have got rid of the cosmetic output. We have two inputs, S and P, smile and punch, and these are all our states. Now we are going to do a little experiment. The experiment is this. Suppose I consider the input word SS, smiling twice in succession, and I want to know what happens if you smile twice in succession starting from a given state. Suppose I start from the very start state, odd. Let's see what happens. The first smile takes it to happy and the second smile keeps it at happy. So if you apply SS, then from odd, ordinary, you go to happy. Well, let's say what happens if you start from angry. First smile, second smile. So if you start from angry, you stay at angry. What happens if you start from furious? First smile takes you to angry, second smile keeps you at angry. So SS causes ordinary to go to happy, angry to go to angry, furious to go to angry. Let's try the other things. What happens if you start with happy? Well, happy remains happy. What happens if you start with surprised? That is also happy. So you see, this SS, this input word, defines a function from the state space to itself. Odd is mapped to happy, happy is mapped to happy, surprised is mapped to happy, angry is mapped to angry, and furious is also mapped to angry. Now let's take another input word. Suppose I take SSS, smiling thrice in succession. Again, I will start with odd, then it will take it to happy. If I start with happy, I remain at happy. If I start with surprise, I end up happy. If I start with angry, I remain angry. And if I start with furious, in that case 3 SS in succession takes me to anger. Observe that both SS and SSS define the same function, which means, and this is very important, that if You have a long input string, lots of input letters coming in S, S, P, etc. And you find somewhere there are two S's in succession. Replace them by three S's in succession, SSS, then the finite automaton will not be able to see the difference. So from the viewpoint of the finite automaton, SS is equivalent to SSS. But if I just try with a single S, that's different. Let's try that out. If I start with odd, I will go to happy. If I start with happy, I remain happy on a single input S. If I am surprised, I go to ordinary. So you see, this column is going to be different from this column. Even without filling in the other things, I can fill in the other things. And if I start with furious, so everything is same except in this entry, because there is at least one entry that is different. So S and SS are distinguishable by this particular finite automaton. So the automaton defines a natural equivalence between the words, the input words. Certain things are equivalent to certain other things, and you should also understand that the total number of such equivalence classes will be the total number of such possible columns. Since the state space is finite, obviously there can be only finitely many such columns. So the total number of equivalence classes must be finite, even though the total number of possible finite length words is infinite. We shall use this to construct our monoid. Now we shall see how we get from a finite state machine to a monoid. We have already seen that certain input words are equivalent from the perspective of the machine. Now club all such equivalent words together, you will get finitely many equivalence classes. Like in our last example, SS and SSS, they will be in the same equivalence class, while S will be in a different equivalence class. Now you take any two words, W1 and W2. Could be, say, for example, you take S and you take SP, something like that. Concatenate them, put one after the other, and you get W3. Now understand carefully that if I take anything that is equivalent to W1 and anything that is equivalent to W2 and you concatenate together, what you will get will be equivalent to W3, simply because when you replace W1 by something equivalent, the machine does not understand. Similarly, when you replace W2 by something equivalent, the machine still does not understand. So the entire process will be transparent to the machine. So whatever new thing you will get will be distinguishable from W3 from the perspective of the machine. As a result, I might say that the equivalence class of W1 concatenated with equivalence class of W2 gives you equivalence class of W3. So this defines a new operation on the equivalence classes, and it is pretty straightforward to check that under this they form a monoid. Why? Where the empty input string, the equivalence class for the empty input string, serves the role of the identity. This monoid captures the underlying structure of the finite machine. Namely, it tells you which are the things that are equivalent. Now, this is in a rather subtle sense. That is why I put the underlying structure within quotations. And it is easy to see that this monoid is always going to be finite because the number of equivalence classes always is finite. So we have a way of constructing a monoid from a finite state machine. It is also possible to do the reverse thing, from a monoid to a finite state machine, and this one is much more easy. You take any finite monoid M together with its operation plus, then we define a finite state machine FSM with state set and input set both equal to M. As always, I am not caring about the output set, which is more like a cosmetic trapping put on top of the structure. Now for any state S and any input I, the next state is defined as M plus I, where plus is this operation. So from any monoid, you can get to a finite state machine. Now this immediately gives rise to lots of questions. For instance, I can ask, suppose I start with a monoid and from that construct the finite state machine. From that we construct again monoids. We have learned how to go from monoid to FSM and FSM to monoid. Do we come back to the same monoid? Or I can ask the opposite question. I start with an FSM, go to a monoid, from the monoid I go to an FSM. Will I come back to the same FSM? Or I can ask the question, suppose I have a finite state machine and I want to know the size of the monoid or some structural behavior of the monoid. So these are all interesting questions. Here is another one. Suppose I have two finite state machines that give rise to the same monoid. Does this mean that they have the same transition diagram? Now this talk is of course not a place where we can go deep into any of these questions, but I can just tell you some of these questions are pretty trivial to answer, but some of them are somewhat deep. So if you want, in that case, you can puzzle yourself with these little problems. We shall not pursue this topic of monoid any further in this video.